So, how does this technology get adopted? And I think we're going to agree on this. I think that, let's make it clear, if you're going to say it's going to be personal transport, which we don't, that's like saying the director of NASA in 1955 goes, hey, look, we're going to build this rocket thing, and the first mission ever is going to fly out to Jupiter, orbit Jupiter, land on Europa, melt through the ocean, and discover life. Yeah, it's that out there. I think that we, like most technologies, a bit like mobile phones, we thought, we never imagined they'd be this good, but we thought they would be pretty good way before they were, right? So similar sort of thing with this technology. I think in limited complexity domains, like industrial autonomy, I think in shuttles in cities where no cities ever asked for more cars, they've asked for less vehicles, where you might have 16 people seaters moving through certain routes in cities, in agriculture, in construction, those domains where the complexity, it's moderate, but it's not nuts, right? Because I think the hardest problem in autonomy is actually prediction. It's not knowing where you are or what's around you. It's predicting what's going to change over the next 5-10 seconds. And in constrained environments that are controlled, you can get more control over that. Here's the other thing. I don't think you have to start by saying I've got to have the whole thing with no operator in it at all. There's augmentation that you can do around safety. So, using radar, where are people that no camera could ever see? Right? Where can I see through dust? You can take parts of autonomy systems and you can use them as you go. So maybe GNSS doesn't work so well on the edge of a field. So you can use radar to augment it there. So I think that you can compose autonomy systems and then we can sell parts of autonomy systems out into the public and generate trust. And I use that word trust at the end of my segment really well, because this tech isn't going to work and be adopted in the marketplace if you can't trust it. And who's going to trust it? Well, regulators need to trust it, users need to trust it, and it needs to make economic sense. And I believe that the greatest innovation in autonomy now comes from new ways to verify and validate autonomy systems. And that's going to be absolutely critical to the adoption, that you can stand behind something and say, yeah, it does use modern machine learning, and that's part of an architecture that gives you the following guarantee. So I would agree with you if you say, oh, it's just deep learning. That's pretty sketchy. But if you say, I'm using the best new technology inclusively in an architecture that also gives guarantees because it might use, for example, optimization, or an architecture that's expecting machine learning to fail, then you can build proper test cases, you can build proper validation, and you can do that at pace. So I think the verification and validation of these systems is the greatest enabler and perhaps currently the greatest barrier to widespread adoption.
It's somewhere between, and we can all create something autonomously that can travel from there to that door pretty consistently, right? And then it's a lot more difficult to have something that's going to travel from here across country and navigate everything. Obviously, it's somewhere in between. That's a large gap. But I think it's really these residential communities, campuses, work sites, even downtown transit circulators, industrial and agricultural environments where you can define a zone of operation, where you can sort of map an area, and you can sort of know all of the possible routes that it can take, so that you can verify and validate that the system that you're deploying there can meet that operational design domain, as they refer to its requirements. And then you can go and test, and there's some methodologies for testing that. I do sort of fall away from the deep learning, machine learning side of the fence, because I think back to the Wright brothers and sort of their approach to controls first and deterministic flight versus those bio-inspired winged contraptions that they had that sort of fell off the cliff. And in many ways, neural networks are a bio-inspired probabilistic approach. And you don't probably want to know that you're going to get to a destination. Ultimately, when you're deploying it, you want to know deterministically that you're going to get there and that you're going to get there safely. And right now, and there may be ways and approaches to do that that I'm not aware of, but right now, we know that in these environments that I just mentioned, that we can verify and validate with the technology that's available now. And I would say heavily GPS INS based. That's one of the reasons why we're here, but also leveraging other technologies that can fill in the gaps. where there may be gaps. But you can find a lot of environments where there's really good GPS, INS coverage, and other things that you can do to the environment to make it so that you can operate in that environment, and adding in this thing that I just referred to, the safety watchdog, that's monitoring the autonomous drive system, such that if something anomalous does occur, you can still fail safe and prove that. And so that's what I think is going to foster adoption, is proving that that this system can operate safely, also lowering the cost of everything.